So welcome everyone to the very last lecture of the first week of React. So it's Matt's turn to tell us something on combinatorial polynomials. Thank you.
Thank you. So congratulations to making it through the week. It's Friday. My plan for today is to sort of talk just a little bit about the research projects that I'm proposing. Number one, to give you a chance to ask questions about them if that's interesting. And number two, to use this as an excuse to show you a little bit of more math, you know, sort of things that are sort of adjacent to these projects. Let me share my screen here. Okay, so there's the first two problems is just in both cases a class of polytopes, and I'm interested in what you can say about them. In particular, I'm interested in what you can say about the Aride polynomials. You know, the first class is a special class of order polytopes that we've seen on the very first day already. And in fact, I talked about this project there. And the second class is about is coming from oriented matroids, which have an intricate relation to polytopes, but in this case, I sort of like I want to turn this around and start with an oriented matroid and you know, take sort of convex hulls of indicator vectors, and so I think people have done this with matroids, you know, without the adjective in front of it, and they've been interesting, these matroid polytopes, and so my hope is there's something interesting for oriented in the oriented matroid case too. And then the third problem is f star vectors. I mentioned those also early on. Yes, this is one basis that maybe has not been studied enough. Yeah, and I wanted to show you a little bit of math, sort of not exactly related to this, but it's connected to that. But I guess let me stop first and see if anybody has any sort of general questions about problems number 1 through 3.
I didn't quite get in problem 3A what is being translated there.
Oh, translating, by translating I mean a change of basis. Okay. Yeah, so I think, why do I say translate? Oh yeah, in the first subproblem, right? Is that what you mean, Anne? So yeah, so this this question is a warm-up question. So maybe you remember. Where's my picture? Yeah, so it's this picture. So this is a picture of all Erhard polynomials, right, in dimension 2, written in the monomial base, standard monomial basis. And by translating, I just mean draw this picture and the other basis. It'll be, the picture is going to look the same. But yeah, like I said, I think this is like a warm-up. And then, you know, to familiarize with yourselves, like, okay, a question like, okay, there will be an array like this too. Yeah. And, just sort of say like, okay, what does F star actually look like on this ray, yeah, in the F star plane. Maybe that was the problem on it. So maybe I should have said for part A, I should have said like, this is just a warm-up exercise. Other questions? So Nick asked about problem number 2. It says we're given an origin matrix on n elements of circuits. We take the vertex set as indicator vectors, and exactly, yeah. So a circuit, right, is a vector. A circuit of an oriented matroid is a sign vector, right? Its entries are plus, minus, and 0. And so what I'm saying is, let's make this an actual, let's make these into actual numbers, plus, minus, 1, and 0. Yeah. And then view them in the correct dimension, yeah, as points in the correct dimension, and then take the convex hull of all circuits. So this will be not a 0, 1 polytope. It will be a 0 plus minus 1 polytope. It'll be a polytope living in the plus minus 1 cube, but it's a lattice polytope. Yeah, and well, okay, so let me, so I had planned to talk about this on day 2, but then run out of time. So let me make a longer remark about abstract simplicial complexes. Yeah. Yeah, so my remark is of the sort, there's, and as everybody who does abstract simplicial complexes knows, there's always a realization of them, but there is actually this realization actually has sort of has nice Erhard properties. So I wanted to mention this at some point. And so, yeah, talking about F star and H star reminded me that I wanted to talk about this. Yeah, so so by an abstract simplicial complex, let me call it gamma. Yeah. So this is a on some set V. I want this to be finite. Yeah. This is just a collection of subsets of V that's closed under taking subsets. And so from this, I get two geometric realizations, and yeah, so this is not my invention, but I wanted to bring this up in terms of the sort of Erhard arithmetic. Yeah, so yeah, so namely, okay, if yeah, so yeah, so if this is a simplex in gamma, yeah, so in the abstract sense, this is just some subset of V, right? Then so starting with the simplex, I can realize this as a unimodular simplex. So maybe we should call this delta of sigma. Yeah. By simply taking the convex hull of the unit vectors in Euclidean space indexed by V. And so I take the convex hull of those unit vectors, you know, let's call them EV, that are indexed by my elements in sigma, correct? And so this is, if you want, this is the standard realization of a simplicial complex. It's expensive in the sense that I am in a high dimensional space, correct? So this lives in R, to the V. And so if V has many points, then yeah, this is, so some people spend a lot of time trying to find geometric realizations that is lower dimensional. But okay, yeah. So if you want, so now maybe we should call this R for realization. So so R of gamma is maybe this geometric simplicial complex. Yeah, so consists of all of these. Then this is now a complex that I can put my hands on. Yeah, and so for this thing I can compute an Erhard polynomial, right? Because so maybe I should say what this is, right? So so if you have, I'm doing sort of the analogous thing when I consider a triangulation as a simplicial complex. Yeah, I just take the union, correct? So so this is I guess the number of integer points. Maybe let's write it like this. Yeah, so where I take the union of all of my simplices. Yeah, and let's say shrink the lattice. Yeah, that's maybe the easiest way to write it. Yeah. So why am I throwing this out there? Well, this is I, for example, can write this as a sum of Erhard. Sorry, this is an Erhard. Yeah, this should be the Erhard polynomial. Yeah. Yeah, and then I mean in this scenario, it's best to think about Erhard series. So the corresponding Erhard series. Yeah, so I can think of my simplicial complex as the disjoint union of the relative interiors. Yeah, so so if I take relative interiors of Yeah, well, this is not very clean. So, if I write the support of my simplicial complex, my geometric simplicial complex, as a disjoint union of the relative interiors, then I'm just summing the Erhard series, right? So, so I'm summing the Erhard series of the interior. Yeah, and so now I'm in a good situation because I'm modeling things with unimodular simplices, correct? So this is what was it, the z over 1 minus z to the dimension plus 1. Yeah, and so if you write this in the right dimension, so I guess this is a v plus 1, then up here you get exactly the h polynomial of the complex. Yeah, so I mean, you've seen this calculation with unimodular triangulations. And the reason why I wanted to show you this is you can model other simplicial complexes. Yeah, so you can model abstract simplicial complexes like this. Yeah, so this is one, and well, I said there's two. So what's the other natural thing to do? Is something that maybe we should call box of sigma. Yeah, so what I want to model is now with cubes, but they're sort of half open cubes. So let me write down the definition first. Yeah, so I'm going to take Minkowski's sums of the unit vectors but I'm making them sort of half open. Yeah, again over all v in the simplex. Yeah, so I'm if these are my if these are the two coordinates that I'm interested in, these are they belong to some two-element subset. I'm considering this sort of half-open square. Yeah. And what makes this interesting is that if you look at the faces, you see another half-open cube, a one-dimensional cube, correct? And so the faces of these boxes of these half-open cubes are again half-open cubes that belong to subsets of sigma, and so this is another model of the simplicial complex. Yeah, and so out of this you get something that maybe we should call C for cube. And so I'm going to collect all of these. And so again, there's an Erhard function. This is defined in the same way. Yes, I'm just computing integer points in here. And so now I'm actually doing this on the level of Erhard functions. So why is this? So so now if I look at this same kind of union. So yeah, so how can I think of one of those half open cubes? Well, I can think of it as sort of like the open, two-dimensional thing, yeah, and then the open one-dimensional cubes, and then I guess that one zero-dimensional cube. Yeah, so again, everything matches exactly. So this is a disjoint union of the support. So you can write the support of this cubical complex as the disjoint union of the Erhard polynomials of these boxes, but now we need to take them open. Yeah. Yeah. And just like before, yeah, so this has a nice form. So this is now a unit cube, right? An open unit cube in whatever dimension. And so that has the Erhard polynomial n-1 to the dimension sigma. And so what's going to happen now is you pick up the phase numbers. So yeah. Yeah, so again, I'm going up to V. And so for each j-dimensional simplex, I will pick up n-1 to the j. So if you want to, this is the f polynomial, yeah, of the complex evaluated at n-1. It depends a little bit how you define the f polynomial. Some people like to change a power there, yeah. But okay. Any questions about this? Okay. So let's go back to the project. So there's a project on something called a spanning polytope. So this is something I wanted to add to what I said in the beginning yesterday. Yeah, so this is my second longer remark today, and that is, I mentioned this a little bit, but I wanted to be a little bit more explicit about it. So there's sort of a hierarchy of lattice polytopes. So, in some sense, this is not about classifying polynomials, but it's classifying families of polytopes. But it's connected. It's all connected. Yeah. And so you kind of heard me saying, and this also connects to Wednesday. So, yeah, if you have a polytope that admits a unimodular triangulation. That's sort of like, this is your sort of like Mercedes-Benz class. Yeah, so these are super nice, and there's they have lots of super nice properties. The next category is polytopes that admit a unimodular cover. Yeah, so this is almost the same thing, except that so you want to write P as the union of unimodular simplices, but they don't necessarily form a triangulation. Yeah, and so you might ask, okay, are there polytopes with unimodular covers, but not with unimodular triangulation? And the answer is yes, but only in dimension 4 and above. And you might think about that. And then this is one thing that I mentioned yesterday. They're sort of like the IDP category. Yeah, so if you remember, we had this sort of construction. Yeah, so there's from a polytope, we constructed this semigroup that I called S yesterday. Yeah, that there's a semigroup spanned by the matrix, sort of like a row of ones, and then I think I called this I yesterday. Yeah, so I is the set of integer points in P. So let's say P lives in R to the D. Yeah, so these are the points. So I'm generating a semigroup with the points at sort of height 1 in Harm of P. Yeah, and so IDP says that this semigroup is the same as the integer points in Harm of P. Yeah, so this is a definition. And again, you can ask, so if you have, I think this was one of our homework exercises, if you have a unimodular cover, then you have IDP. And so again, you can ask, are there IDP polytopes that don't have a unimodular cover? And the answer is yes. And for this, you have to go into dimension 5. Yeah. So these are subtle things happening here. And the next category, so there's various things that I'm ignoring here. So you can make my picture, you can make this finer, but the next category that I find interesting are very ample polytopes. Yeah, so what that means is that so in general, the semigroup S lives in this other semigroup, the integer points in Harm P. And so you might say, okay, if they're not equal, what's the difference? And if the difference is finite, that's a definition of a very ample polytope. Yeah, so some of you know the phrase very ample from algebraic geometry, and there's a connection. This is where the word comes from. Well, okay. Yeah, so I claim IDP, well, not I claim. So IDP means that this difference is 0. So, that's a subset, yeah. But you can come up with counterexamples for the other inclusion in dimension 3. So this is actually not super hard, not as hard as the other counterexamples. But so now you can ask other questions. I mean, you can ask other questions with the other stuff too, but so this is something. This is actually my unique joint paper with Matthias that we wrote a couple of years ago. You can ask, okay, the points in here, so the points in here, they're called gaps. Good. Yeah, it's a good name, right? So they're the integer points in Hom of P that are not generated by this other semigroup, by this other by the points in P. And so so you can ask the following question. Where can these gaps be? So here's your height 1. This is where your polytope lives and your integer points. So they're all there. But then the typical thing that happens is at height 2 in your Hom cone, you have most of your gaps. And so one question we asked back then is like, can these gaps be arbitrarily high, or is there sort of a bound on how large they can be? So if you start computing very ample polytopes that are not IDP, all of your gaps are on height 2 in this Hom cone. But so we came up with some constructions that are sort of extreme examples where those gaps are sort of very high in the cone somewhere. Okay, and so here's the last thing in the hierarchy that I wanted to talk about is spanning polytopes. And this is connected to this project. And again, you can find a sort of counterexample to the other inclusion in dimension 3. So what does spanning mean? So now I'm doing some sort of construction just on the level of polytopes. So what I do now is I stay actually in dimension D, and I see what I can span just from the integer points in P. And spanning means, so let me assume that this is full dimensional. And spanning means that these integer points now Z-span everything. If your polytope is not full dimensional, then you would replace this with the affine span of P intersected with the lattice. And you can convince yourself that a very ample polytope is spanning. And so, so this class is interesting in the following sense. So this is a class that has only been named a couple of years ago. But it's interesting in several ways. So it's sort of it's a very mild condition, so so a spanning polytope is not sort of a generic lattice polytope, but it's it doesn't have that many conditions, but people realized so this class came up because there were some known sort of H star inequalities that only holds for IDP polytopes. Okay, this was a paper from, I think, the 90s. Yeah. And so some people looked at these inequalities, and they realized actually you don't need IDP to realize these inequalities. They actually hold for spanning polytopes. Yeah. And so this is an interesting situation, right? So you have some extra constraints that hold for a subclass of lattice polytope, but then you want to get down to the details and say, like, okay, what is it actually that I have to assume? And it turns out for those inequalities, you only need the spanning condition. Yeah? That's one thing. And the other thing is, the other interesting thing about non-spanning polytopes. Okay, so yeah, so non-spanning polytopes, and this is what this project is about. Yeah, so a non-spanning polytope, yes, that means that sort of knows now two lattices, right? So for that, I can compute an Arrowhead polynomial. Okay, I can compute an Arrowhead polynomial, whatever, H star, yeah, and so on. Yeah, but I can compute another Arrowhead polynomial, and namely, I can think of my polytope. So maybe I should call this the Erhard wiggle polynomial. Yeah. I can think of computing lattice points not in Z to the D, but computing lattice points in here. Yeah. So if I have a non-spanning polytope, that's a different lattice. Yeah. It's isomorphic to Z to the D again, so I can do the whole Erhard thing. Yeah, and my polytope lives in there. It's a lattice polytope in that lattice. Yeah. And so non-spanning polytopes come with two interesting Erhard polynomials. Yeah. And yeah, so in this second lattice, they are actually spanning. Correct. I mean, I'm defining this second lattice in such a way that in that lattice, P becomes a spanning polytope. Yeah. And so, once I have a spanning polytope, yeah, I have these inequalities and so on. Mm-hmm. And so, yeah, what I'm curious about is what this project number 4 is about. Basically, is how different can these be? Yeah. So I mentioned, it would be interesting to have examples where the H star polynomial in one version is unimortal, but in the other version is not. Yeah. And this has to do with conjectures that are out there. So, for example, one conjecture says that H star polynomials of IDP polytopes are unimortal. That's an open problem. Okay, so this project allowed me to show you this hierarchy. This is really, this is less about polynomials and more about polytopes, but it's related, like I said. Any questions on this or on project number 4?
Can I ask if those about the strict inequality, the strict containments you get,
Mm-hmm.
Is dimension 5 known to be the lowest in which that happens, or could it be that there is something in dimension 3 or 4, for instance?
I think it's known to be the lowest, but don't quote me. Yeah, so this is I believe both of these are in papers sort of in the early 2000s by Bones, Kopeladze, and co-authors. so not just one paper, where they sort of made this a program to really sort of figure out what's going on here. Yeah, and so there's a lot of connections to algebraic geometry, K-theory. There's sort of like a K-theory of polytopes, and commutative algebra. Yeah. So yeah, like I said, the phrase very ample already comes from algebraic geometry, and these sort of hierarchies when you start computing things. It's very useful to switch between fields. Yeah, so so some people asked me about this already, earlier this week. Like, there are toric ideals and toric varieties that come with lattice polytopes. And so the notions of, like, very ample, having a unimodular cover and so on, yeah, and this can be translated in this language. Yeah. This is super, I think this is super interesting stuff. I haven't done much, as you can see, on this, but this is very, very cool stuff. And I just saw that Xiang Ying posted a link. Thanks.
Thank you.
I think the first, so they wrote a series of papers. I think the first paper was with Chung. That's the most famous paper, but don't ask me what they proved in there.
Can I also ask a question?
Yes, Lawrence.
So talking about connections with other subjects, sometimes I hear people calling IDP polytopes normal, but then someone else tells me, no, there's a slight difference, and I quite forgot what the difference is. Can you?
Yes. The difference only appears when your polytope is not full dimensional. Yeah, so if your polytope is full dimensional, the definition of normal and the definition of IDP are the same. And if your polytope is not full dimensional, I also forgot what means what. Actually, if you look at my paper, my unique paper with Matthias, I remember that we wrote about this because we had some polytopes. We dealt with some polytopes that are not full dimensional, so we had to worry about it. Yeah, but this is a couple of years ago.
I see. Thank you.
That's right. Alessia just said it has to do with the lattice that you're considering. That's exactly right. That's exactly right. So one notion is I even forgot this, but I know Alessia is correct because I mean, anyway, I should just shut up. Yeah, she should look it up. Yeah, so the word normal again comes from varieties, correct? There's such a thing as a normal variety. And so, people usually talk about normal polytopes, they mean IDP. Not realizing you have to be careful when your polytope is not full dimensional. Yeah. I prefer the phrase IDP because it tells you what you're doing. You're decomposing, you're integer decomposing your polytope. Okay, shall we drink some coffee? Okay, any questions that came up over coffee? Okay, so my problem number 5 is about quasi-polynomials. It's something, well, okay, let me tell you where this comes from. So this connects to what we said at the end of yesterday. So in some sense, what's the easiest way of coming up with a generating function, that gives rise to a quasi-polynomial is if I start out with something like 1 over 1 minus z to some a times 1 over 1 minus z to the b or something like this, okay? And then, yeah, and then, well, I need to make this into this sort of standard form. So, this will be, this p over here will be then at the end the LCM of a and b. Yeah, and you have some nice thing sort of appearing in your numerator. And it turns out these very, very simple generating functions are there are generating functions of Erhard quasi-polynomials. This is related to some number theory called the restricted partition function. And yeah, this is in some sense, you can produce these generating functions from first principles. Okay. Now, what I'm curious about is if you then put them into this standard form and then expand, using our H star basis, so you expand now maybe in an artificial way in terms of binomial coefficients and so on. What can you see from that point of view? That's the philosophical question behind problem number 5. Okay. Anybody who has a question about that or wanted to talk about problem number 5? Okay, and then the last problem is again something I wanted to spend some time on, like a longer remark, and it connects to the stuff from yesterday. I said sometimes it's good to move back and forth from this sort of geometric world to this world of semigroup algebras and try to think about things a little more abstractly, and this is motivated by a conjecture in graph theory. It's called the Antimagic graph conjecture. And it's the following. All of you know magic squares, right? So there's an example there on the right. So a magic square. You have every row and every column, they have to sum to the same number. And I guess for the original magic squares, you also have the diagonals, but I think I'm ignoring them right now. Yeah, I'm ignoring them. Yeah. And it turns out there's sort of like an analogous concept on graphs. Okay. So in graphs, this is a following thing. You put labels on your edges of the graph. And you want the sums of these labels at each node to be the same. And so this is called the magic labeling of the graph. And in fact, what you see here is a graph model of a magic square, again, without the diagonals. Yeah, so you have 6 nodes because I have 3 row sums and 3 column sums. And the edges correspond now to my entries. I have 1 edge for each row and column pair, correct? And so getting a magic labeling of that graph is the same thing as getting sort of a magic labeling of my square. And so, what's an anti-magic labeling? Well, it's again, again, you label the edges. So label the edges. And you want to use the labels 1, 2, 3 and so on. Every one exactly once, such that the vertex sums are now distinct. So such that the sums of the labels at each node, at each vertex, they're distinct. Magic would be that they're the same, and so now I want them to be different. So let's try. So here's my favorite graph, K2. Okay, here's the only way to label it with numbers from 1 to number of edges. So on the left you have vertex sum 1, and on the right you have vertex sum 1. That doesn't work, and the conjecture is that this is the only counterexample. So every graph, every other, and by other mean not K2, and I guess I want it to be connected. Admits an anti-magic labeling. So this conjecture is from the late 80s. And so it's one of those notorious conjectures in graph theory that there's some results sort of like, if you have enough, I forgot, if the degrees are big enough or something like this, you can do that. So the situation is pretty bad. This is open for trees. So there's not that many conjectures in graph theory that are open for trees. So anyway, so this is a cool conjecture, so let me describe an answers to that sort of wraps around to the first day when I started talking about chromatic polynomials. So what did Birkhoff say? Like for chromatic, for the 4-color theorem, right? So you should try polynomials, right? So let's do that. So let me introduce now a function. Okay, A for anti-magic, and I'll put a little star on top of it for no really big reason. So so this is a function of some parameter n. And so what I want to count is the number of anti-magic labelings. and I'll tell you in a moment what I mean by that. So Antimagic, let's call it an N labeling. Yeah. Of the graph, yeah. And so by Antimagic, right? So okay, so up here, so again, let me say, like, what we're going to use is exactly, right? Labels 1, 2, down to cardinality of E. And so I want to have a parameter over here. And so that's not true anymore. Yeah. So what I mean by this is I'm going to use the labels, use any, I guess, distinct. Yeah. So any E labels from the set 1 through N. Yeah. So I have a parameter now that says, yeah, I don't need to use the first E numbers. I can use the first N numbers. I want my labels to be distinct, and I want the sums, the sums at the vertex, at the vertices to be distinct. And so the antimagic graph conjecture now says that, okay, in this counting function, if you plug in the number E, you get something non-zero. Yeah, everybody with me? So far, so good. Okay, so why am I doing this? Well, there's geometry behind this concept, correct? So just like, so I hope I convinced you that there's geometry behind the chromatic polynomial. So there's geometry behind this counting function. So so these labelings, they live in a cube, correct? I have I guess, just like in the chromatic case, let me take the open cube from 0 to n plus 1. So this is the cube in dimension, in the edge space, correct? I have one label per edge. And each label is between 1 and n. And so, I'm going to model this with an open polytope, and that polytope will be the unit cube dilated by n plus 1, and I'm going into interior. Okay, so that's first of all. And well, they're off some hyperplanes, correct? So what are we not allowing? Well, we're not allowing two labels to be the same. So we take out the braid arrangement in this space. So that's one. So now my labels are distinct. And now the other one is, right, sort of like labels around an edge, right? So E, I guess, incident with a vertex V. That sum should not be the sum of labels edge E incident with W, where now VW is an edge. Sorry, no, I didn't say this right. V and W are just two nodes, two vertices. Yeah, so any two nodes should have a different sum. Okay, so just like in the graph labeling case, so you take your cube and you chop it off into smaller polytopes. Yeah, and so now you know why I wanted to make that cube initially open, because now I take out these hyperplanes, so I get so this is a union of rational polytopes. Yeah, so all of this, this is some union of polytopes. And they're at the very least rational, right? They're given by constraints with integer coefficients. Okay, what does that mean? Well, that means this thing here is a quasi-polynomial. Guaranteed. Okay, what's the degree? So, well, we live in E space, right? So that's that's the dimension, and so this quasi-polynomial should have degree number of edges. Yeah, so there's some analogy here to the chromatic polynomial. So, except that for the chromatic polynomial, the degree was number of vertices of the graph. No, it's number of edges. Yeah. And okay. Yeah. Does this setup make sense? So let's see a little bit what happens. Yeah. So again, sort of like this is like the situation with the chromatic polynomial situation. The chromatic polynomial and the four-color theorem and so on. But there's two differences. Yeah. So now we have degree of our, of our counting function. Well, the quasi-polynomial is E, and we want to know. What happens when you plug this degree in. Yeah, so this is different from the chromatic polynomial. Yeah, the chromatic polynomial for the four-color theorem, you have a polynomial of degree whatever, number of vertices, and you plug in the damn number 4, right? That's so now here, this is kind of like more in line. Yeah, so maybe we should call this nice. And number 2. So now you start computing and you say, okay, is this really a quasi-polynomial? And so here's an example. So this is for a cycle with on 4 nodes, and indeed, you have a quasi-polynomial. Yeah? So this is, come on, you can do it. It doesn't want to write anymore. No, I really don't. Okay. Yeah, so this is not a polynomial anymore. It's only. Yeah. Too bad. Yeah. So why is this too bad? So Yeah, so let's think about a little bit what happens with this counting function, yeah, from one end to the next. Yeah, so if I think about, okay, how many possible anti-magic labelings can I produce when my parameter goes up? Well, I only have more freedom, correct? So this has to go up. Yeah. And I claim, okay, so you can check this, yeah, this just from the geometry, you can prove that your quasi-polynomial is 0 when you plug in 0. This basically comes from the fact that at 0 you're computing sums of Erhard polynomials of open polytopes at 0. Yeah. Yeah, and so what does that mean? Yeah, so I claim this now means that if this function was only a polynomial, so if this were a polynomial, we're done. Yeah, so, and I claim when you plug in E, you get something non-zero. And let me convince you why. So, so what do we have here? So here we have a root. And what are we saying over here? Well, if this is a positive integer, if this is a root, then this also has to be a root. Yeah, your function can only go down, and at least on positive integers, you're still counting something, right? Yeah, so you have a polynomial of degree E that can have at most E roots. Yeah, and so if 0 is already a root, yeah, the worst case scenario is that 1 is a root, 2 is a root, 3 is a root. Yeah. But once you plug in E, you're out of roots. Yeah. So, now you know why I draw this face over here. Yeah. So, if this function were a polynomial, then we're good. Okay, so what can you do? Well, it turns out you can salvage something. You can salvage something, and that is if you get rid of this condition over here. So if you forget about having to use distinct labels, you can prove something. So you can prove that this quasi-polynomial has period at most 2. And when your graph is bipartite, it has period 1. That means it's a polynomial. The bipartite case is interesting because trees, for example, are bipartite. So you can say something smart about bipartite graphs, and you can say something smart about trees. Yeah, so if this condition is if you allow us to repeat labels on the edges, we still have this sort of anti-magic conditions on the nodes, but on the edges, you allow us to repeat labels, then we can sort of prove a version of this conjecture. Okay, one reason why I wanted to show you this is I wanted to tell you how you go about something like this. So well, okay, before I give you a little bit of details on this other construction, let me pause for questions. Are there any questions about the setting or about this idea? Okay, so let me make a connection to what we did yesterday. Yeah. So okay, so here's here's one answer to compute this. Well, this is really an answer to compute. So let me call this just A for antimagic. So this is the number of antimagic n labelings with repetition allowed. Yeah, so I mean, I could have the same label on two different edges. And so, okay, maybe I should say this first. Yeah, so where is there sort of like the Erhard structure? I told you this is, we have sort of the union of polytopes. Yeah. So now, if I want to use semigroup algebras to address this, what happens? I can only do this on a given polytope. Yeah. So the structure as a whole is not a semigroup structure, because you have these forbidden hyperplanes. Yeah. So if I have a polytope, then I homogenize, I get a nice semigroup structure, but now I take some stuff out. And so I might be in the case where I have 2 points in the polytope, or in the cone rather, over the polytope that are not on those hyperplanes, but if I'm adding them, I end up on one of those hyperplanes. Yeah. So I don't get the semigroup structure to begin with. I have to do some tricks. And one way to do that is to just realize, okay, I can write this as sort of an inclusion-exclusion sum. Where I look at sort of partial magic labelings. Yeah, and so my sum will be over subsets of the vertex set. Yeah. So what do I mean by that? So if you want to compute, if you want to see antimagic labelings, let me just throw down all possible labelings of my graph. That those have a nice form and I can count them. So just all edge labelings, I guess, of my graph. And then I have to take out all edge labelings where I have the sum at one node equal the sum of some other node. I would call this a partial magic labeling, because there's these two nodes in the graph that I know want to demand that the sums of the labels around the edges are equal. And so I'm going to subtract all of these and I have to include back all partial magic labelings where I say the sums at 3 vertices are the same, and so on. So okay, so that really suggests that now I should say, okay, let's count those. So I don't know, maybe this is like a sum m for magic. And this really depends on the graph, but it also depends on a subset. Yeah, so let me take a subset of my vertices, and so now this says count. Yeah, so to count the number of n labelings that are sort of magic, at S. Yeah, so that means that if you look at the nodes at S, you want your sums of edge labels around those nodes to be the same. Yeah. And that's a semigroup structure now. Yeah, so think of your graph, whatever, here's your graph. And you want to look at all possible labelings where the sum here and the sum here are the same. Yeah, and for the other ones, I don't care as long as they are between 1 and n. Yeah, if you take two such labelings and add them, you're going to get another partial magic labeling of your graph. Yeah. So this is a semigroup structure now. It's still a polytope structure too, right? So this is still an Ehrhart quasi-polynomial that I'm counting here. Yeah. And now I'm just in one polytope. Yeah. But so now I have sort of like a chance of going back and forth in those two worlds. Yeah. Yeah. So because there's now a polytope there, right? I mean, a polytope is kind of funny, right? So you have whatever 1, 2, 3, 4, 5, 6. You're in 6-dimensional space, right? But you have one equation. Yeah, so I guess your polytope is 5-dimensional. Okay, for this graph, it's probably not so hard to write down the polytope, yeah, but think of your graph as like really complicated, high degrees in the vertices and so on, yeah. And so now, I'm basically asking, okay, what do the vertices look like of the polytope? Yeah. Whereas on a semigroup structure, so now you can say, okay, give me my the completely fundamental elements, of the semigroup. So what is an element of the semigroup? Well, it's some labeling of my graph, that cannot be decomposed any further. Something like I don't know. I put a 1 here, a 0 here, maybe I don't know, a 1 here and a 0 here. And I don't care what's happening down here, so this would definitely be an element in my semigroup, right? It has equal sums of labels at those two green nodes, and I guess this cannot be decomposed further. I think this is one of the completely fundamental elements in this semigroup. So can you see what I'm doing here? So I'm realizing, okay, this thing is an Ehrhart polynomial, a quasi-polynomial rather. In fact, this is actually a polynomial, but okay, we don't know that. Let me just say it's an Ehrhart quasi-polynomial. But instead of saying, hey, let me try to figure out like, what this looks like, is let me go in this other world, where my Ehrhart series lives. This Ehrhart series comes from the semigroup, and understanding the semigroup means I have to understand these completely fundamental elements, and those are labelings of a graph, right? So now I can draw graph pictures. You can try to figure out what these look like. Okay, this was a whirlwind. This is a whirlwind about anti-magic labelings. Any questions? well, I should say what the project is. So project number 6 is an idea to put this back in. Yeah, so let's put this this distinctness requirement of the labels back in. And in a sense, think very carefully. Okay, maybe we shouldn't go into the unit cube. Okay, maybe I shouldn't live here. Yeah, but I should live in one of the regions defined by the braid arrangement. Yeah, this is sort of a natural idea, I hope. So what I'm saying is like, okay, this unit cube gets chopped up by both these equations and then those. Okay, but let me forget those second ones first. Like let me do this first, and actually now go into one piece. So now I'm in a simplex. In fact, you've seen that simplex when we did unimodular triangulation of the cube. Yeah, and so let me just try to understand in one of those simplices what sort of the antimagic labeling look like in that thing. Yeah. And I really want to leave the orderings of the variables sort of general, but I want to think of them as ordered in some way. That's the last project. Okay, any last questions? We got 3 minutes. Yes. Ariaman asked about the reference. So this is not in my book. The whole connection with the graph coloring and so on is in my book with Raman. Maybe you've seen this already. On this Antimagic stuff, I have a paper with Mariam Faramat. Yeah, it's there we go. Thank you, Sampara. This is where we do this construction for where we allow labels to be repeated on edges. Yeah. So this would be your starting point for that project.
Okay, thanks. I'll check it out.
Sure.